CompGran is an acronym spelled out as compaction and sound in granular matter, and the experiment targets the measurement of the dynamics and the time evolution of a granular material that is loosely floating around in space without sedimenting. Typically, you could assume that granular materials are the second most used substance class in industry after water. Imagine pharmaceutical ingredients, imagine food. Many things in our everyday life and in industry come in granular form. And it's surprising that the physics understanding of granular matter is relatively far behind regular fluids. Many things in granular media still require an awful lot of testing and on-site planning and experimenting. And we want to support the theoretical modeling, the understanding of granular materials in a way that maybe in a couple years or decades we can calculate many of the granular problems we today need to figure out by trial and error. What we measure is we have either a highly agitated granular material where the particles are flying around and collide, or something that is becoming progressively slower because as the collisions take energy out of the system becomes slower and slower. And when you shine laser light on that, you get reflections of the interference patterns, and those interference patterns reflect what the sample is doing dynamically. First of all, and I think that's clear to every child, if you play with sand, which is a prototype granular medium on Earth, you cannot have sand float around for more than half a second in front of your eyes. That's why we do experiments in microgravity, and in preparation for the space station experiment, we have run preparatory experiment on drop towers in the parabolic flight and even some experiments on sounding rockets. So that allows us to look for an extended amount of time at the motion of these granular particles before they sediment, which would happen majorly on Earth. One of the little bit surprising results from the CompGran experiment on the ISS is that we can observe for very much longer time that the system is becoming denser and denser, and this could not be observed on ground naturally, but this can also not be observed in the seconds and minutes of the suborbital platforms. So we agitate the sample and then we gather data and statistics for the behavior of the particles in the sample, and that is sort of characteristic for an unsedimenting motion of an agitated granular system. We would then have a couple minutes where we wait until the system and the particle dynamics comes to rest. We then observe that over days and weeks, the sample evolves into becoming denser and denser and denser. That is fascinating because that progresses over many, many runs, and it can continue if you stop the experiment and go back to it after a couple of weeks. The hard part is to make a precise experiment and a suggestion how to really analyze and measure those different behaviors. And let's say we had our first parabolic flight using that laser scattering method in 2009. Over the next couple years, we did things on parabolic flights and in the drop tower. And it was then decided in 2012 that we could be on board of the nice machine soft matter dynamics that's shared between foam investigations and granular matter dynamics. And that matured over the years and was put on orbit then in 2018 by the German ESA astronaut Alexander Gerst. And since then we have been measuring multiple times per year actually, and we are still busy investigating all the outcomes and analyzing all the data and interpreting what we have learned. One of the beautiful applications of laser scattering is that you cannot only investigate things in the laboratory, but you can go into an industrial process. If you imagine filling a bag with your material and you want to sell it, one thing you want to avoid is having a lot of fine dust, because that's a health issue, and it's also forbidden by many regulations in recent years. While formerly industry was pulling out samples from that big bag, you now want to continually monitor your process, and doing external diagnostics similar to what we developed for the space station is an ideal way of making sure that you can not only make individual measurements for individual samples, but is a good way of monitoring full processes and assuring that you can avoid unwanted fine dust being produced in your process, for example. Over the last years, it's been an amazing journey to go from the laboratory experiment through the parabolic flights and drop towers all the way to the space station. So that has involved people from industry, people from ESA, people from the B.USOC, making sure that in the end we have a good protocol to do within a short amount of time an effective run of measurements. And I only can thank ESA, Airbus, the B.USOC and the German Space Agency DLR for selecting the experiment, for helping us mature it, for financing both the scientific and the engineering part. And we are very happy to look further at our results.